Hello and welcome once again on the lecture series of course Elements of Machine Design. Myself, Mr. S.S. Mari, Head of the Department Mechanical Engineering, Sharath Institute of Technology, Polytechnic, Edra. Once again, I welcome all the students. Right now, we are in the lecture number 5. Up to lecture 4, we have seen the introduction of the syllabus. We have seen what is meant by the machine design, what is meant by the stress, what are the different considerations of the machine design, how to design any machine element, that is the procedure for machine design. In previous lecture we have seen what is meant by the stress, what is meant by the strain, and what are the different types of the stresses. In last lecture we have studied two types of the stresses, that is the tensile stress and tensile strain, and compressive stress and compressive strain. In this lecture we will see remaining stresses. So let's start. The next stress is the shear stress. Now what is meant by the shear stress? As I have told in the last lecture, the tensile and compressive stresses are the direct stresses. That means when we apply a load, direct load, that is the tensile or compressive load on the machine element, then there is a possibility of induction of tensile and compressive stress. Now the next type of stress is the shear stress. Now when a body is subjected to two equal and opposite forces, that is the same case as the tensile and compressive stress. That is when the body is subjected to two equal and opposite forces acting tangentially. That is most important requirement. When the body is subjected to two equal and opposite forces which are acting tangentially across the resisting section, due to which the body tries to shear off the section, then the stress induced is called as the shear stress. That means when two and opposite forces, now these are the two equal and opposite forces which are acting tangentially. Now this is the rivet and these are the two plates. Now these two plates are joined by this rivet, what is shown in figure. Now this is the resisting section. Now this is the portion of rivet, that is the cylindrical portion, and these are the two plates, one at the top side and one at the bottom side. When these two forces amount P is applied in opposite direction having the same magnitude, then this section, this body tries to shear off. This is the shearing, tries to shear off. Now this rivet, due to this force, came to this side. This rivet, due to this force, came to this side. Now this is the resisting section, that is the shearing section. Then the stress induced due to this kind of a mechanism is known as the shear stress. As we have seen already in last lecture, the basic fundamental definition of the stress, that it is the resistance per unit area to the applied load. So this is the resistance of breaking due to the application of load on these two plates. As these two plates are joined by a rivet having diameter small d, hence when these two and equal opposite forces acting on these two plates, this riveting section tries to shear off, that is the shearing. And this, due to this phenomena, this resistance offered by this section is the shear stress. Now the shear stress and shear strain are denoted by a Greek letter tau. Now this is the notation for shear stress, tau. As we know that we have seen that stress is denoted by sigma. In the same way, the shear stress is denoted by a letter tau. Mathematically, the shear stress is the tangential force divided by resisting area, that is the force per unit area. That is the definition of the shear stress. And this is the mechanism of the shear stress. That is when it shear off or the forces acts tangentially across the resisting section. Now take this concept. It may be noted that when the tangential force is resisted by one cross section. Now this is the one cross section of the rivet. Then the rivets are said to be in single shear. Now this is applied force. This is applied force. Now this is the rivet and this is the resisting section. Look at this. This will happen after the shearing off. Now this is the resisting area. This is the resisting area. When this rivet shear off, we will look like this. The entire section will look like this. That is the shearing off section. In such case, the area resisting shear of rivet is, now this is the area resisting shear having diameter small d. This is the rivet having small d as the diameter. Now this is the resisting area. In last lecture, as we have seen that the most important part is the resisting area. It is the cross sectional area. So this is the diameter d. Now its area, cross sectional area, this is the resisting area, and its resisting area is given as we know that the area of the circular part is given as the pi by 4 d square. It is having a diameter of small d. So tau is equal to force, applied force, that is the tangential force divided by resisting area. Now resisting area is this is the resisting area. So we can write tau is equal to P upon applied force as pi by 4 d square. So this is the shear stress induced in this rivet section due to the application of this tangential force P. So from this we can determine the amount of tau, that is the stress induced by just arranging these terms. That's tau is equal to 4P upon pi d square. Now in this case, if we know the value of tau, we can determine the value of d, and if we know the value of d, we can determine the induced stress in this system. So in simple language, shear stress is defined as when we apply a tangential force across the element, then the resisting section get shear off. This is the action of shear off. Now this type of stress is known as the shear stress. This is the action of the shearing. Now crushing stress. What is meant by the crushing stress? Up to this point we have seen tensile stress, compressive stress, and shear stress. Now we will study what is meant by the crushing stress. Crushing means it is a contact between two points. When there is a contact between two elements, then there is a crushing of some tiny particles in between that two elements. So crushing stress is nothing but a localized compressive stress. We know that when we compress something, then there is an induction of the compressive stress. Means when we apply a compressive load on any element, then there is a possibility of induction of compressive stress. Now crushing stress is nothing but a localized compressive stress, means at a particular point. When we apply a particular load at a particular point, that is the compressive load, then there is a resistance offered by that section is known as the crushing stress. It is at the surface of contact between two members of a machine part that are relatively at rest is known as the crushing stress. A simple example of this crushing stress is nut bolt. If we tight some bolt with a nut mechanism, then at the surface of the bolt and the nut there is a crushing stress, because it is a localized compressive stress at a particular point, at a particular part, at a particular periphery. That is the crushing stress. The crushing stress is taken into account in the design of riveted joint, as we have seen, quarter joints, knuckle joints, etc. Now have a crushing stress. How we can determine the crushing stress? In last lecture we have seen how we can determine the shear stress. Now have a look how we can determine the crushing stress. Now again the same example that we have taken when we have understood what is meant by the shear stress. Let's take an example of a riveted joint. Now this is the rivet. This rivet is joined by these two plates, upper plate and bottom plate. This plate is having a thickness of small t. This rivet is having diameter of small d, and the force applied have a value of P newtons. Now when we apply the P type of force on this element, then this is the diameter. Now this is the diameter of rivet which is shown here, and this is the thickness. This is the thickness of rivet. Now this is the cross-sectional area which actually shows the crushing. Crushing will take place at this point, at the contact between this plate and rivet, at the contact between the plate and rivet. Now this is the diameter. This is the diameter of this rivet, and this is the thickness. Now this is the thickness. Now the resisting area will be dt. T is the thickness and D is the diameter. Please try to understand the concept of crushing stress. In simple language, if we just have a nut and bolt arrangement, then the crushing stress will get induced at the contact between the nut and bolt. Now at that point, we have to consider the length of nut, that is the thickness of nut, and diameter of that bolt. Now D into L or D into T will be the resisting area. Same logic is applied here. D is the diameter and T is the thickness. So we can have D into T as the resisting area, and N is the number of rivets. This N is the number of rivets. Suppose there is a single rivet, then the simple D into T is the resisting area, P is the applied force, and then according to the definition of the crushing stress, we can determine crushing stress as the force upon resisting area. Force upon resisting area, that is the crushing stress, sigma C. That is the notation for the crushing stress. So this is the concept of crushing stress. In simple language, we can say a crushing stress is nothing but a localized compressive stress which will cause due to the contact between two parts which are at rest. That is important. Now next concept is the bearing pressure. Now crushing stress is also known as the bearing stress. Now have a look at the bearing pressure. In last concept, that is the crushing stress, we have seen that it is the compressive stress which is a localized stress which is caused due to the component at rest. But this is a bearing pressure or bearing stress, or what we can say bearing pressure. The bearing pressure is caused due to the rotation. Now this is the shaft and this is the rotating journal having diameter D. This is the fixed bearing having length L. Now it may be noted that local compression which exists at the surface of contact between two members of a machine that are in relative motion, that is most important. In crushing stress, we have seen that both the elements are in rest position. But in case of bearing pressure, that is the concept of bearing pressure, I can see here. In case of crushing stress, we have seen force upon T into D, that is thickness into diameter. But here this is the length of journal and this is the diameter of rotating journal. And this rotating journal is in contact for this amount of length with the fixed bearing, and this is the rotating, and this is the fixed. So between the two members of a machine that are in relative motion, in one may be fixed, another may be rotating, or both may be rotating, is called bearing pressure, not the bearing stress. It is the bearing pressure. This term is commonly used in the design of journal supported in a bearing. Pins for levers, crank pins, clutch lining, etc. Now let us consider the example. The journal exert, now this journal, rotating journal, exert a bearing pressure. This bearing pressure on the curved surface of the brushes. Now this is the distribution of bearing pressure on the surface. The distribution of this bearing pressure will not be uniform as seen in the diagram, but it will be in accordance with the shape of the surface, in contact and deformation characteristics of the two materials. The distribution of bearing pressure will be similar, that is shown in the diagram B. Since the actual bearing pressure is difficult to determine, therefore the average bearing pressure is usually calculated. by dividing the load by dividing the load to the projected area. Now L into D is the projected area of the curved surface in contact. Hence we can write a bearing pressure as force upon projected area L into D. Again keep in mind, bearing pressure is different and bearing stress is different. It is the pressure exerted by the rotating element on a bearing, that is the bearing pressure. That is the localized compression which exists at the surface of contact between two members of a machine or part that are in relative motion is called bearing pressure. So this is the concept of bearing pressure. Now let's move towards the concept of bending stress. In simple language, the stress which is caused by the bending moment. Now let's have the concept of bending stress. Stresses due to the bending moment. Now take a simple member. Now take this is the shaft. Take a simple shaft. This is the simple shaft. And suppose if we apply the load like this is the application of load on a shaft, then there is a induction of this bending moment in the direction, upward direction, anti-clockwise direction. Bending moment, we know that bending moment is given as force into perpendicular distance. Now suppose this is the value of P, force P, which is acting on this shaft. Then this is the say distance L between these two. Then this bending moment will be given as P into L because it is acting at the end of the shaft from the center. So this is the P into L will be the bending moment, and due to this bending moment the stress induced in shaft is known as the bending stress. The stress which is induced in shaft due to the bending moment is known as the bending stress. Now this is the distribution of bending stress. This stress will be minimum at the neutral axis. This is the neutral axis where there is no stress. That is the neutral axis. Now take into consideration, when this type of a stress will occur, then the upper portion will be under compression stress and lower portion will be under tensile stress, because this shaft will move in upper direction from both the sides. Due to this, these fibers, the fibers below this neutral axis will get in tension, and the fibers above this neutral axis will be under compression. When this member will move in upper direction, then the elements which are below fibers will under tension and the members which are above fibers will be under compression. Now see, now this is the shaft. Now this is the force P which is acting here. This is the force which is P which is acting here. Due to this there is a induction of bending moment in upward direction. Now this is the neutral axis where there is no stress. Now fibers below this neutral axis. Now these are the fibers of that shaft. Now these are the fibers of the shaft above neutral axis. Now, fibers below neutral axis will get strengthened in upward direction, means there is a tension in the fiber which are below this neutral axis, and the fibers above this neutral axis will be under compression. That is shown here. These fibers under compression, these fibers under tension. So this is known as the bending stress, and this is the distribution of stress. When we take section, suppose this is a rectangular bar, then this will be the stress distribution, and if this is a circular bar, then this will be the stress distribution. Keep in mind. Now we can give the bending stress as a bending moment into Y. Now this is the Y, this is Y, this is Y. Y is the distance from the neutral axis. Y is the distance from the neutral axis. I is the bending moment, MB is the bending moment, I is the moment of inertia, Y is the distance from neutral axis, and MB is the bending moment. Now bending moment is given as the force into perpendicular distance. Now for rectangular section we know that moment of inertia is BD cube by 12, and for circular section we know that moment of inertia is the pi d raised to 4 divided by 64. By putting this value in this equation we can determine the bending stress. Now B is the distance of parallel to the neutral axis, B width, and D is the distance perpendicular to the neutral axis. Okay, so this is regarding the bending stress, the stress which is induced in the element due to the bending moment, and bending moment is nothing but the force into perpendicular distance. That is the concept of bending moment or stress due to the bending moment, that is the bending stress. Now this is the stress due to bending moment. Now let's have a look at the stress due to torsional moment, that is known as the torsional shear stress. The stress due to bending moment is known as the bending stress, and stress due to torsional moment is known as the torsional shear stress. Now take a simple example, a transmission shaft. This is the transmission shaft having length L. It is subject to an external torque. Now this is the external torque, MT is the external torque, also known as the torsional moment. Just imagine this end is fixed. This is the fixed end, and this end is subjected to a torsional moment in clockwise direction. This is the clockwise direction. This end is fixed. Now this element is subjected to a torsional moment in the torque is acting in the clockwise direction. The internal stresses which are induced to resist the action of twist. Now this is the resisting action. Take into account. Just understand how this resisting action will take place. Now this end is fixed. We are applying a torque of amount MT on this. That means we are applying actually force. We are twisting this. We are actually twisting this shaft. But this shaft is resisting this twisting. This shaft is resisting this twisting, and due to this resistance, the stress which is induced in the shaft is known as the torsional shear stress. Try to understand. When the transmission shaft is subjected to an external torque in clockwise direction, the internal stresses will get induced, which will resist this action of twist. Now this shaft will twist through amount of theta. And this is the angle through which this shaft will get twist, that is the angle of theta. Now as we have seen in the last in previous slide, the bending stress is given as MB, that is the bending moment, into Y divided by moment of inertia. And the same way this torsional shear stress is given as torsional moment into R d by 2 divided by J, that is the polar moment of inertia. Now MT is the applied torque, tau is the torsional shear stress, R is the radial distance of the fiber from the axis of rotation, that is the radial distance. This is the radial distance, that is we known as the radius, and a polar moment of inertia. In case of bending stress we have taken moment of inertia. In this case we are taking the polar moment of inertia about the axis. Now as we have seen the stress distribution in bending stress, that fibers above the neutral axis and the fibers below the neutral axis. Same stress distribution will take place in case of the torsional shear stress. Now this is the equation of torsional shear stress, keep in mind, which is important from the which is required for the solving the problems. And we have seen the equation, that is bending stress we have seen the equation of bending stress. This is the equation of bending stress, which is also required for solving the problems. So bending stress get induced due to the action of bending moment, and torsional shear stress get introduced due to the action of this torsional moment. Now as I have said to you that this shaft will twist through an angle of theta. Now this theta is given as, angle of twist is given as moment, that is the torsional moment, into L divided by J, that is the polar moment of inertia, and G is the modulus of rigidity. L is the length of shaft. The polar moment of inertia for solid shaft is given as pi d raised to 4 divided by 32. Last slide we have seen the moment of inertia is given as the pi d cube by 12. Now pi d raised to 4 by 64. and this is given as the pi d raised to 4 by 32, and for hollow shaft it is given as the pi do raised to 4 minus di raised to 4 divided by 32. Do and di is the outer and inner diameters of the hollow shaft. So these two equations are very important. That is the equation of torsional shear stress and equation of bending stress. Again, torsional shear stress is caused due to the torsional moment, and bending stress is caused due to the bending moment. I hope we have understood what is meant by the stresses, that is the torsional shear stress, bending stress, shear stress, crushing stress, and bearing pressure. Now this is the basic equation of power, how we can calculate the power, where m suffix t is the torque which is acting on this shaft. Thank you.